This is Jason McIntosh with McIntosh Applied Engineering. In this video, I'm going to show you how to use a graphing feature called cursors. It's available in all of the graphs in Aries, not just the modeler. But to show you how to use it, I am going to use the modeler graphs. It is consistent throughout all of the graphs you find in Aries, though. So here's a graph from the modeler. To create a cursor, you'll right-click, and close to the bottom it says New Cursor. When you click on that, it's going to create a cursor close to the area where you originally right-clicked. Now we have this square cursor. When you move over top of it, you can left-click on it and drag it around. It shows you the current position of the cursor in the legend up here. Here the cursor is given a name cursor 1 and its position X and Y coordinates. As you drag it around, it'll track the curve you're closest to. If you go up to another curve, it'll jump up there and snap to it, and it'll snap to the bottom one as well. You can create as many cursors as you want. You right-click, select New Cursor again, and here we have one on these curves. The cursors have a wide range of options available for them. To edit the options, you can move over top of the cursor and right-click and select Edit Cursor, or you can right-click anywhere in the graph and go to the Edit Cursor menu and select which cursor you want to edit. They all have names. Or you can just simply move over top of it and double-click with the left mouse button, and that'll bring up this dialog box. I'll take you through the options for the cursors. First, it'll auto-generate a name for you. I'm going to change the name to diff. You can tell it to show the name next to the cursor so that you can keep track of what cursor is what with their name. So I'll go ahead and select that and click OK. Now next to this cursor it says diff, and in the legend it's reporting the coordinates for diff. So I'm going to open up the editor again. Just below that, you can manually select a color for the cursor, or you can have it take on the color of the curve that it's been snapped to. I'm going to go ahead and change the color to purple, and I'll make it nice and thick. Give it a line weight of 4 so it's visible for this video, and click OK. So here's our new color for our cursor. As you move the cursor around, there's a number of options for its mouse behavior. The default is to just snap to the closest curve. However, you can tell it to stay fixed to a particular curve. If I select that at the bottom here, this drop-down list box here lets you select which curve you want it to be fixed to. I'll go ahead and select the second one and hit OK. So now the curve is on the second curve, the green one, and as I drag it along, it won't leave that green curve. So the cursors are handy for instance, let's say you want to know what the frequency of this peak is. You can move it over top, and it's 3.8 kilohertz or so. You can find out what the minimum is, about 5,300 hertz, so forth and so on. The next option I'm going to show you is there's a feature where it'll only track the data points in the curve, or you can interpolate between the data points. To show you how that works, I'm going to move up to this. Actually, I'm going to let it snap to any curve. I'm going to move up to the red one. It's a little peak here there. And I'm going to zoom in around that peak. And so now you can see the individual discrete data points for this curve. If I grab that cursor and move it along, it just snaps between those data points. That's usually what you want to do. But if you want to interpolate between them for some reason, you can turn this snap to data points off, click OK, and now when you grab the cursor, it'll just smoothly interpolate between all the data points. There's some instances when you want to do that. When you have a lot of curves on the graph, it can be confusing as to which curve the cursor's on. So you do have an option to have it show you the name of the curve next to the cursor that it's on. So go ahead and hit OK. I will. So right now it's telling us we're on IEC 711 measured Z. I can auto scale this, and as I bring it down to this curve, it's saying we're on the 711 model, and we're saying on the current buffer. So it'll tell you what curve you're on. This is a pretty tame set of curves, so it's fairly easy to see which one it's tracking, but sometimes it's hard to see. Go up and open the options again. You can also just have it drag to an arbitrary position. So I'm going to select drag position, hit OK. And now when I drag it, it's not snapping to any particular curve, but it'll move anywhere you want to put it on the graph. I'm going to go ahead and I'm going to set this back to snap to the closest curve. And this one, I'm going to show you what happens when you go to a fixed position. When you have a fixed position, you can't move the cursor at all. It's just fixed there. But typically when you fix the position, you'll come down here and you'll type a particular coordinate you want to be at. Let's say we want to be at 1,100 dB. Press OK. So it's moved the first cursor down here now. So this is a fixed point for that. Where that's useful is with the next option here. Actually, let me show you something else here. So you can not only show the position in the legend, but if the legend is getting kind of busy, you can turn that off and you can show the position next to the cursor. So I'll go ahead and click OK. So here we are. It's telling us what cursor it is, its diff, what line it's snapped to, and its current location. And it's not reporting its coordinate up in the legend anymore. So it's makes the legend a little less busy. I'll go ahead and open this one up and turn that off as well. So now the position for this cursor isn't even being reported anywhere on the screen. So we've gone through the different mouse behavior that you can use. Now you can also have it show you the difference between the location of your current cursor and one of the cursors that you can select from this drop-down box. So this is the diff cursor, diff up here. So let's go ahead and plot the difference with cursor 1. And by default, it's going to show it in the legend, and it's going to draw a line between the two cursors. So I'm going to hit OK. Here's the line connecting cursors that are being differenced. And as I move this along, it's reporting the difference between diff and cursor 1. So right now they're 272 hertz apart and 14 dB apart. And you can go ahead and move this to various positions. This is handy if you want to, for instance, find the 3 dB down point in a curve, let's say. I'm going to make this a snap to a curve. I'll go ahead and put this in kind of the mid band. If we want to know the 3 dB down point relative to the mid band here, we can move this along until the cursor reads, I'm looking right here now, until the cursor reads minus 3 dB. So the 3 dB down point is about at 232 hertz or so. So there's an example of how you can use difference. You can tell it to show the difference location on the screen between the two curves and not show it in the legend, again, to unclutter the legend a little bit. So here it's reporting the difference between the two curves. There is a way to copy these numbers out. I'll show you that after I cover the next section, so I can show you it all at one time. All right, I'm going to go ahead and edit this. I'm going to turn differencing off for now. I'm going to move on to curve fitting. Frequently, when you have a cursor, you not only want to know information about its absolute levels, but what's the behavior like around the cursor and in through the graph, so forth. So there's some curve fitting or analysis options. First one in the list is just a simple slope. I'm going to go ahead and select that, hit OK. When you perform a curve fitting operation, each cursor then that's having a curve fitting done has a start and stop range that you can grab and expand. So here it's computing the slope of this curve over this range. As I grab onto that cursor and move it around, it'll go ahead and track that data and come up with its best fit for the slope for that range. So if I narrow this up a little bit, it'll track these differences a little better. So there's a way of getting the slope of the curve, which can be useful at times. If I go back now and I tell this cursor to just have an auto select of the color based on the line it's snapped to, notice that it can be kind of hard to see the curve fit line there. So that's one of the advantages of setting this to a different color. So you can see how the curve fits fitting a little better. And as I drag this along, it's showing the slope here up in the legend. As with the other options, you can tell it that you don't want to plot the coefficients in the legend, but you want to show it next to the cursor. That will again unclutter the legend a little bit if it's getting a little busy. That can be important if you've got a lot of graphs, a lot of curves being displayed at once. So here it's reporting the slope now underneath the cursor. This option lets you plot or not plot the curve fit curve. That might be useful if you want to do a final plot or something and you don't want the curve fit curve cluttering up your graph. Okay, so that was the slope. One of the things, there's an option here where it has a scale curve fit range for log x axes. I'm going to turn this off to show you what that does. When you turn it off, you can manually enter the range over which it's going to perform the curve fit from the cursor, plus or minus, shown here. So if I want it to be minus 100 hertz to plus 100 hertz, I can just change it to that, hit OK, and so now these range bars go 100 hertz from the cursor. Now on a log scale, as I grab the cursor and I move that around, notice that when I go to higher frequencies on a log scale, those plus or minus cursors disappear to almost nothing. And for the slope, it's reporting error, need more data points. These two, the min-max range are so close together, it's not picking up enough data points to compute a slope. But as you move it to lower frequencies, they'll expand again. And then when you go to very low frequencies, they get kind of ridiculously big. So this behavior is really annoying if you're typically doing curve fits on a log scale. So to compensate for it, this option is set by default, which will scale their range based on a log x-axis. So we'll go ahead and hit OK. If it's a log x-axis scale, now it'll keep the apparent distance of the min-max range constant for a log scale as you move it around. The actual min-max range does change. It won't be plus or minus 100 hertz anymore, but at least it'll stay kind of geometrically the same range on a log scale plot. So if I move it out here, click on it, and now I've got minus 2000 plus 2000 instead of plus or minus 100. But you'll typically want to use that. And if this is a linear scale, it won't change their distances at all. It'll just keep the constant plus or minus 100 hertz or whatever you had entered in. Okay, there's two more slope options here. These assume that your y-axis is plotted in dB. The cursors aren't smart enough to know whether this is a dB scale or not, so you have to be aware of that. If it is a dB scale, it'll show you the slope in terms of either dB per octave or dB per decade. This is useful for when you want to see how many poles are in your system. So for instance, if I move this down here, it's showing a slope of about 25 dB per decade. So there seems to be about a single pole down here. To show this off a little better, I'm going to move the graph to the output of this speaker here. Bring the graph back up. So now our current buffer is shown in blue here. And at low frequencies, our slope is closer to 40 dB per decade, which would be 2 poles. And that's typically what you see for a radiating speaker. So again, the dB per decade or dB per octave is handy to determine how many poles you have in your system. So if I change it to dB per octave, it's now reporting 12 dB per octave, which is again 2 poles. And you can adjust the range over which it computes that slope, of course. It will also calculate min and maximum for you. I'm going to do the min and max value first. So I'm going to show you how it computes maximum value. Now it just looks over your curve fit range and it reports the maximum value, which is in this case at the maximum curve fit range. And the max value is 98 dB at 318 hertz. So this is more handy when you go next to a peak. So as you move it around that peak, the max remains fixed at that one data point, which is 351 hertz and 123 dB. You can copy these numbers out for pasting into a document if you want, instead of trying to copy them down just by looking at them. You can right-click on the cursor, and then there's a number of copy features here. First one is copy current position. So if I select that, I open up a notepad, bring notepad open, right-click, paste, there's the current position of that cursor. If I right-click, I can select copy curve fit parameters to clipboard. If I come over here, right-click again, paste, there's the curve fit parameters. The maximum is at 651 hertz and 123 dB. Or you can copy all of the current data to the clipboard. Come over here again, right-click, paste. There's the position, there's the max. And had we had the difference feature on, let's go ahead and turn that on. Well, difference with cursor 1, hit OK. Now we select copy all data. Right-click, paste. There's its position, there's its delta with the other cursor, and there's the curve fit parameters, the max at 651 hertz. Turn differencing off. We can also report the minimum value. Go ahead and click OK. So if I'm sorry, select maximum again, minimum. If I drag this over to this curve here, it'll report the minimum for this dip. It's occurring at a little over 5300 hertz, and it's 96 dB, and it doesn't change as long as the curve fit range is within the range of that minimum value there. It has another min-max function for computing the min-max of a location. This one uses a quadratic equation to curve fit to the data over the range. So I'm going to go ahead and move it up here, and notice that our curve fit now is it's actually a parabola. It'll go according to x squared. And if I scooch this up, I'm going to go ahead and zoom in here. And if I really want to know what the peak is here, and I don't want to just trust that one data point, I can zoom in here, try to curve fit to the data as best as I can, kind of smooth it out. And this seems to be a good fit to the data. In this case, it's reporting a maximum value here of 123 dB, but now it's at 655 hertz. If it just went on that one single data point, let me snap to the data points again. If we just went on this one single data point, that occurred at 651 hertz, whereas the polynomial curve fit is saying it's actually 655. Very close because we have a lot of resolution to our data, but if you want to get a little bit more accurate idea of a minimum maximum, you can use this quadratic curve fit. It's fairly handy. Let me auto scale this out. And now it's reporting a max, but if you go down to a valley such as this, it will automatically see that that's a minimum down there, and it'll report the minimum for you. So it switches between max, a max and a minimum based on what it sees with the curve's behavior over that region. The next curve fit option is a little more complicated. It'll fit the data to an arbitrary polynomial. So I'm going to select polynomial, and now you enter in the polynomial powers in this field here. Right now, it'll be just a linear curve fit, y equals x plus some constant. To explain how these polynomials work, you enter the polynomial powers here. This would be like P1, P2, P3. And it's going to curve fit y to x to one polynomial power, x to another polynomial power, so forth and so on. And then it'll show you what these coefficients are. It'll calculate y1, y2, y3. So you enter P1, P2, P3 up in this edit field here, and then Aries will curve fit these coefficients to the data. One special case is if the polynomial powers are just zero, just one value here, zero. In that case, you just compute an average, and then y will just be y naught, y zero. Let me show you that. So I'm going to bring the graph up, and I'm going to set the polynomial to be zero. This just computes an average again. So if here's our range, and I'm moving this around, the average value of y is, in this case, 99 dB. If I go down, it drops. If I go up, it goes up accordingly. So if you want to know what like the mid-band level for this response is over this range, it's about 113 dB over that range. So that's one of the uses of just a polynomial power of zero. If you want a linear fit, you can just enter 1, 0. This would be a linear polynomial. Click OK. And this is very similar to what the slope does, but this will give you, yes, this fits the data to y equals x plus some constant. Now, because this is a log scale, that linear function is curved and bent around. It'd be a little easier to see if this was a linear scale. When I go ahead and change it to a linear scale, click on the graph, do linear x, go back to the graph. Things look a little goofier here, but you can see what the linear fit is a little better uh, on a linear scale. You can, I'll make it a quadratic, put a power of 2 here. This is basically what the curve fit with a quadratic did, except now it'll report the powers for you about how well it curve fit over a particular range. So here are the powers listed here. I'm going to go ahead and put that back in the legend. So here's the powers up in the legend. It shows you how well it curve fit. It isn't going to compute the min-max for you with this, but at least you can see what the polynomial fit looks like over a given range. And you don't have to enter just integers. You can enter fractions if you want. If, for instance, we entered 5, 0.5, negative 0.5, well, 5 would be x to the power of 5. 0.5 would be the square root of x. Negative 0.5 would be 1 over the square root of x. So in this case, it'll report y2, y1, y0 based on these powers. Why don't we go ahead and do that? So we'll do 5, 0.5, negative 0.5. It's kind of a goofy polynomial. It doesn't particularly mean anything to me, but it's just kind of give you an idea of what all this can do. So if we broaden this out, that's how that polynomial is being fit to the data. And obviously, if you want more, if you want a different polynomial or more powers, you can do that as well. So if I want to see what this looks like with, say, 5 orders here, we can do 5, 4, 3, 2, 1, 0. That'd be a 5th order polynomial fit. And there's how it's fitting the data. And it's reporting all the polynomials, coefficients for you up in the legend right now. One thing about these cursors are that they are temporary. If you save your Aries file, the cursors won't be saved. They're just attached to the graph while that graph exists. If you delete a graph and bring the graph back, it won't bring the cursors back, so you'll lose the cursors. These cursors are meant to be temporary, quick ways of getting more information off the graph, not a way of permanently documenting your data. And I believe I mentioned that you can delete a cursor by right-clicking and selecting delete, or right-clicking anywhere, going to the delete cursor menu and select delete, in this case cursor 1. So I've only got one cursor now. It's fairly easy to add different curve fitting options up here. The final curve fit option is shown here. This is a special case that is used mostly with nonlinear behavior of porous materials, but it shows that we can add different curve fit options here. So if you have an interest, let us know. How this works is it assumes the data looks roughly like this, where for small values of x, y is just a constant value. Then there's some transition point at x1, and after x1, it'll go up with a constant slope of dy. So this equation is fit to the data for the last curve fitting option. But again, I show this mostly because we can add different curve fitting options to this list here if you have a special need. So just contact May and let us know. So I hope the cursors are of interest to you. If you have any questions, please feel free to reach out and contact us at May. And I want to thank you for your time.